There's no mic. Okay, hello everyone. I'm going to share my screen and we are going to talk about Google Maps. So this is a topic which is interesting for me. So I thought maybe we can talk about this system design. There are lots of interesting aspects and use cases that I think it's interesting. We can learn a lot about it. Okay, first of all, what's the purpose of this system application? It's help to find directions and then navigate to destinations. That's two main important use cases. So then I think if we wanna list a couple of functional requirements, we can come up with a couple of requirements. But before than that, it's always good to ask few questions about the business, especially when we are interviewing. We can ask this question from the interviewer or more question. I'm thinking of a couple of questions like this. For example, how many daily active users do we have? This is a question that we can ask for many system design problems. So let's say we have 1 billion daily active user. And then what features are we going to support? Location update, navigation, ETA, and map rendering. Let's focus on these four. Location update, it means that when a user, whether it is walking, they are walking or whether they are driving, they need to send their location updates to server, like in some intervals. We'll talk about it more. And then navigate. Navigate means that we want to go from point A to point B. ETA, so like server needs to send the client, the user, what is the estimated time to get to some destination. And then map rendering. Map rendering comes to talking about how we want to download the bold image in client's, let's say, mobile phone or desktop. That's an important piece of this system. Number 3, how big is the raw data? These are some questions that we can come to understand the scaling of the problem. So that should be terabytes of data. That's all road and cities and I don't know, areas of the whole map of the world. So that should be terabytes of data. Number 4, for accurate ETA, should we take into consideration the traffic also? Yes. Do we need to support different travel mode, like driving, walking, whether by bus or car? The answer is yes, we need to consider these different modes as well. Do we need to support multi-stop directions? For now, for simplicity, no. And how about business places and photos? Do we need to go for it? Do we need to have them as part of the maps? Again, for simplicity purpose, I'm not going to talk about that piece yet. Non-functional requirements. Non-functional requirements, first of all, accuracy is super important because we don't want to get lost. So accuracy is important. Smooth map rendering and navigation is also important. We don't want to download the whole image of the map in client's, let's say, device. Obviously, we need to think about it and provide some smooth map rendering. And as a result of that, smooth navigation. The system should be highly scalable. We are talking about terabytes of data, 1 billion daily active user, and also it should be highly available. Okay, then let's talk about map projection. How we are going to deal with the map of the whole world. There are a few mechanisms and strategies and algorithms that are commonly used. One is geocoding. We get an address. Let's say we want to go from address A to address B. So both addresses, first of all, they need to be mapped to latitude and longitude. So this process, this mapping is called geocoding. And that is something that can be done offline and can be stored as an static data, so that it doesn't have to be calculated every time. Number two, geohashing. Convert each area on the map to a string. When I'm saying each area on the map, let's say with this small picture here, I'm trying to demonstrate what I'm talking about. This is, let's say, the map of the world. So that needs to be divided to smaller areas, and then we assign, let's say, binary numbers to each piece. Let's say the first area is 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and then again, the let's say 1, 0 is also divided to smaller pieces. Then it goes to like 0, 0, 0, 0. Then accordingly, we come up with some binary representation of each area. And then this binary representation can be converted to any other format. And the result, the geohashing, the geohash will be a string of, let's say, letters and digits. So we divide map to a smaller area until we reach to a certain size threshold. Then map rendering. Map rendering is going to be done by map tiling, similar to what I explained above. The map of the world will be divided to smaller pieces, smaller pictures called tiles, and then each tiles, and this should be based on which zoom level that a user selects. Let's say in zoom level first, we have only one picture, which is the whole world, and then let's say level 2 will be more data, more tiles. It depends on how detailed view of map a user needs to look at. So for each zoom level, we store static set of tiles and pictures. Again, these can be static data, and we don't need to calculate or generate these data server side. It can be done offline and then stored in some sort of storage, object storage, or CDN. I'll talk about it more. And then navigation. Okay, so from one of the functional requirements were navigation. Navigation, we can use some algorithms like similar to digester algorithm, which finds the shortest path from a source to destinations, different destinations. Here, particularly one destination we are interested about. Then road data map needs to be converted to a graph. This road data map is different from the map picture that I talked about. That's in static data. Those are the pictures. These road data map are different. These are about like information about roads, about places, about these data needs to be converted into a graph model. Nodes are in which nodes are intersections and edges are roads. Graph needs to be broken into manageable units using geohashing. Again, these graph, similar to what we talked about map rendering, raw data, this, let's say, huge graph needs to also be divided with the same mechanism that I explained above into smaller units. And save the information, map their information in, with their geohashing code. Then routing tiles will be loaded on demand. Let's say a user is driving, and depending on which location the user is, then we only need areas around that particular location. We don't need to download the whole map into client's device, which is not performant, obviously. And then also to reduce, this is for reducing memory usage, and as a result, increasing path finding performance. Let's talk about some estimations. When we are talking about estimation, I would like to focus on two important pieces. One, estimating storage, and second, estimating throughput. Okay, let's talk about storage. That is, we talked about at least just one piece of data that we need to store is map of the world. And then, which by itself is huge. As we talked about, there are different zoom levels. Let's say just in one zoom level, we might have 40 trillion tiles. And if each tile is 250 in 250 pixel, let's say it is 100 kilobyte, then 4 trillion tiles in 100 kilobytes will be petabytes of data, which is huge. And there will be some metadata to be stored. We can ignore about it. It's not sizable in compared to other piece of data. And this and the third is road information. As I talked about raw data above, so that's also huge, terabytes of data. So obviously, it's clear that single servers, single databases won't be enough. We will need to handle this with distributed servers. And another estimation I want to talk about is throughput. Throughput, there are two different requests in this system. At least for the functionalities that we decided to work on it. So one is navigation request. And second is location update request. Navigation request, it's that, okay, one user needs to go somewhere and they open the app and request to go from location A to location B. In order to see, let's say, estimate how many navigation requests we will need. Let's say we talked about the daily active user. We have 1 billion daily active user. Let's assume each user navigates only, let's say, twice a day. Then we come to 2 billion navigation requests per day. And then 2 billion requests divided by 10 to the power of 5, which is seconds in a day. It comes to 200,000 requests per second. 20,000 requests per second for just navigation requests. And then about location update requests, we have 1 billion daily active user. Let's say each of these daily active users are online for 30 minutes on average. It means And let's say every second we are sending a location updates to the server. So it'll be 30 billion requests per day. And then if we want to avoid 30 billion requests per day, which per second, it will be 300K requests per second. And let's say in peak times, it is 10 times. So it comes to 3 million requests per second. And if we want to avoid sending these location updates to the server every second, let's say we decide to go with every 10 seconds, and then we will come to 300K requests per second, which is still a huge number, a high throughput. From all these estimations, it is clear that throughput is high and processing powers, also similar to storage, needs to be distributed. Now I want to talk about a high-level design. Very high-level design, if we want to design this system, is we have a mobile client. So first of all, they need to open their app and get the map rendered into their device. So we can use CDNs, which gets map images, tiles for every zoom level from, let's say, CDNs, or maybe if CDNs are costly, maybe we can go with object stores. But anyway, we get the map images from a CDN, a location near to client's location. And then we have two important microservice, one navigation service and one location service. Obviously, we will need a load balancer to route requests and to appropriate services. And as you might know, load balancers, they do a lot. They can not only route the request, they can they come up with some security features, firewalls, rate limiting, and all that. So again, if we are using cloud, this can be something similar to AWS Gateway, which is inherently scalable, and it comes with caching and firewall and security features, as I mentioned. Then let's talk about navigation service. Location service. Navigation service is responsible to find the best routes, and then it fetches the geocoding data, which is a key value database, something similar to Redis. That's just a map of addresses to latitude, longitude of user locations. And then also routing data can be stored in an object store. Those graph data structure that I talked about. Then navigation service also works closely with ETA service. And ETA service gets the traffic data from user location database, which is updated and written into with a service called location service. User location updates come in streams of data. We can talk more about it, but for now, this is high-level design. Then they are stored in user location DB, and they can also be cached in in-memory cache, something like Redis or any other cache mechanism. So this is high level. if we want to talk a little, we want to deep dive into more details, let's focus on location service. I want to point out a couple of interesting areas that we can talk more about location service. We said that we'd better to batch updates in some time intervals, and that will be more efficient than sending location updates every second. But even doing so, we will still have a high ride traffic. For such high ride traffic, there are a couple of considerations we should think about. First, we should use some stream processing platforms such as AWS Kinesis, I don't know, Kafka, that I will talk about the structure of it later, but for now it's better to have some sort of stream processing here. The other thing is that we should use a high rate optimized DB, such as Cassandra or DynamoDB, which are also highly available. This is high write heavy scenario, and we need to think of some databases that can handle high writes, high write traffics. Consistency, availability is super important. Scalability is super important here, but maybe consistency is not as important. It comes next. So then for scalability, obviously this data needs to be distributed and needs to be sharded, and we can then think about, okay, what data, what key needs to be used for sharding. I'm thinking of user ID plus timestamp, user ID as partition key and timestamp as sort key. If we are using something like DynamoDB, this can be easily defined, and then DynamoDB is a AWS service, which can be scalable automatically behind the scene, and we don't get involved with all the physical work, but anyhow, sharding is the key here. Third, for communication protocols, if we want to talk about the protocols, which protocol is efficient, efficient and preferable here, right? I'm talking about sending up location updates and to be written into database. Because these are very constant data, ever coming data, first I'm thinking about WebSockets, but WebSockets maybe is a little overkill because that's a two-way protocol. Maybe just using an HTTP with keep alive option is enough. So that we do not need to open and close the connection all the time, which won't be efficient. Users are constantly moving and they are constantly sending their location updates. We need to come up use some protocols that is efficient for these huge stream of data. If we want to talk about API design, let's say we have a post REST API, which is similar to this, version 1, location, and the parameters will be latitude, longitude, and timestamps. And location data will be stored here in a table which contains these fields: user ID, latitude, longitude, timestamp, and mode. Is it driving, walking? And also I could add another live status if the user is active or not. But this is some few data that we need to store into our database. Gathering this data is important to build a live and historical traffic data. This traffic data is important. ETA service can be leveraging it to send, accurate timing to clients. So we need to keep this data, even the historic data. If I want to talk about that streaming processing that for updating location data, actually this location service, or actually these are all distributed servers. These are not just one service, but if I want to talk more details about it, location service will have a front service which get the information, a stream of data, send it to it pops up, let's say, message queue. This can be Kafka or any other message queue. And then from there, it's also be consumed with a couple of different consumer services, let's say analytics, machine learning, microservices, let's say for personalization. And also the most important for our use case is traffic update workers. And because I think that we want to scale our producer, which here is this location service front service, and our consumers, we need to scale them independently. We are using this queue messages and async design. Similarly, maybe like not all these services have the same scaling capabilities. So it's better to use as needed. I'd rather to use another message queue, point-to-point message queue, that these workers, again, this is not just one server, these are the workers which subscribe to this message queue and use these messages. And then write the location data into Cassandra or DynamoDB that we talked about. Here, okay, looks like we are getting out of time. So I need to be a little fast. So this is this is location service. Navigation service is about finding the efficient path from A to B. Some API design similar to get V1 nav from origin address 1 to destination address 2, and method is deriving, and the response will be, okay, here is the distance, here is the duration and instructions. As I said before, navigation, we use routing data, which should be cleaned and converted to graph, and that needs to be done offline, in offline pipelines, which always run in the background and capture route changes. Then this data is broken into tiles. How do we store this database option is S3 object store that can be fetched by Geohash, and Geohash can be mapped to geocoding value of latitude and longitude. With better to cache routing data in memory extensively to reduce latency. Okay, here is the navigation detail. There will be a front service which gets the geocoding data from a database, and then key value database, and then send it to a route planner. Route planner can talk to a ranker, which also talks to, let's say, filtering service, how to avoid tours, how to avoid, let's say, highways, those kind of filterings and optimizations, and then find shortest path through this service. And then this service is actually using that graph data that we talked about before. And then this adaptive ETA service. Adaptive ETA service using traffic update services that we said before. It is updated by location service. Actually, this location service gets data from location DB and then update traffic DB. And then adaptive ETA service can read traffic data from location service and send it back to clients. And because this is from server to client, that needs to be some sort of protocols that uses server to client data transfer, something like WebSocket, service side event, or push notification. And finally, map rendering. Map rendering, we don't want to generate map tiles on server side, as I said, which is expensive. Instead, we have static pre-computed map images for all zoom levels, which can be downloaded to client per navigation and as needed. Advantages of this is we fetch images through HTTP requests directly from nearest CDN servers. The static nature of tiles make it highly scalable. That's why we want to go with pre-computed static images. Client data usage should be kept low. We can consider client-side caching for performance. And at the end, costs also should be considered when we decide to go with CDNs. CDNs are expensive. Maybe we decide to go with some sort of cloud object stores, which is another option. Something like S3, blob storage, Azure blob storage, or anything similar to that. Okay, we can continue talking about more advanced features. Let's say, how about multi-stop navigations? Something that is used and useful in the case of Lyft, Uber, DoorDash, those type of applications. But I leave it here, but that's something to think about. That's all I have to say. And I hope it is useful, and I'm open to questions. Moji?
I have a question about that ETA service, the communication between ETA service and navigation services. Go down.
Okay, here.
Yes, here. How do you communicate between these services, adaptive ETA services and traffic data services?
Yeah.
Communicate through the HTTP here or other service-to-service communication?
Yeah, this is a good question, actually. This can be HTTP, but these are internal services within, let's say, our system. We can go with some other, like communication protocols as well. Let's say for performance, we can go with gRPC, which is suitable for internal services communications. But HTTP would work as well. I'm calling it adaptive ETA service because it's this traffic data is constantly being updated with this traffic update service. So maybe we want to reroute. We want to send another ETA, updated ETA to users. That's why I'm calling adaptive ETA service. But do you think of any other protocol that we can use here as well?
No, I just thought about the gRPC, maybe the best option here because it's an internal communication plus we need the raw data. We do not.
Yeah.
Traffic data through the binary, it's better than just converted everything to HTTP, then go back again to binary for the computation through the navigation algorithms.
Yeah. Okay.
Another question that I have, could you go scroll up?
Yeah.
Why we need the column-wide database store here for traffic data? Why we do not use some simple document-based database?
This is because I was talking about Cassandra. That's what Cassandra is, a wide column store database. And the reason is that I think we need an optimized, this is a write-heavy application, right? And we need a database which is optimized for writes. And from, let's say, from the databases I know, Cassandra is one of them. That's why maybe that white column was just like a label for this symbol that I use, but I'm thinking about Cassandra here or something similar to that. That's why.
Something similar, such as, for example, can we use the MongoDB here? If not, why? Because MongoDB, the writing throughput for MongoDB also it's good. Cassandra or other column-wide database has their own purpose. We are not using them for the high throughput write.
Yeah, but they are optimized for writes. Like, let's say transactional databases, they are optimized for reads, but not for writes. We will need, that's why we always go with, let's say, I mean, if needed, we go for write replicas versus read replicas. But something like similar to Cassandra is optimized for write heavy applications. But again, I think MongoDB would work as well, but we just need to make that into consideration. That needs to be optimized for write, because that's a stream of data, huge set of data that we need to insert and update constantly. That is like the ratio of write is so high for this application.
Okay. And another question, could you scroll up? Can you tell me about that? How do you generate the graph for navigation? You talked about that. We have a tile.
Yeah.
Created tiling based on use that tiling and geohashing.
Yeah.
Created some association between latitude and longitude to the tile. But yeah. Can you clarify how do you generate the graph based on this information that you have?
Yes, this is done in an offline with some offline pipelines. First of all,